Hello, my name is Jonas Nelson. I'm a senior software engineer at Dovetail Games.
Hi there, I'm Jonathan Quinn, technical director at Dovetail Games. Okay, so imagine you're approaching your cert windows and you get a bug report that performance has dropped 20%, a strange subset of your quests no longer work, or you're getting crashes on a platform that you don't QA as regularly as you know you should. Testing may not sound like the most glamorous of topics, and it's probably not why many of you got in, but it might be one of the most important things overlooked when building them. Getting past the initial overhead, it almost always means more actual time to make your game, and it always means less stress at the end. Auto testing, as implemented in UE4, means useful results with pretty minimal effort. So this is an introductory talk that explores our early journey into auto testing. We hope that for those of you new to this, you'll leave today able to write some simple tests, get some meaningful data from your game, data that might just help you ship on time or with fewer bugs or performance issues. For those of you not new to this, we also discuss our in-house automation pipeline, our approach to presenting data in the studio, and we discuss our future endeavors. So Dovetail Games is a mid-sized developer and publisher based in Chatham's historic dockyard in Kent in the UK. We make simulator games with as much faithfulness to the subject matter as possible. We've worked with UE4 since 4.3 when we prototyped our first UE4 title, Eurofishing. At the time, fishing and UE4 were both pretty new to us, and we used the project to de-risk our follow-up work on our train sim franchise. Our train sim franchise was an existing and popular product, and we didn't want to risk that too much. At Dovetail, we employ lots of people who are deeply passionate about the subjects of our sims, and plenty of other people that are just passionate about making amazing games. The simulator space has seen enormous growth in the last decade, and UE4 has allowed us to capitalize on that, letting us efficiently build and test detailed sims in huge, rich environments. So what is automation testing? Well, it fills the role of both functional and performance testing for us. This is not test-driven development. There is no evaluation of the inner workings of your game. You're treating the game almost as a black box. Auto testing might be a good place to start your exploration into testing, as it's inherently very encapsulated. There was also a great talk on this topic last year from Jessica Baker at Rare, which is definitely worth a watch. So what do we test? Our current set of daily tests focus on regression. So we test FPS and frame times, min, mean, and max, at specified and procedural locations generated all over the map over fixed time intervals. We measure memory usage, we measure load times for all compatible content, and we test a selection of gameplay meta features, so progression, achievements, that sort of thing. We test nightly builds on all of our shipping platforms, so PS4, Xbox, and PC, and all that data from testing these builds is then aggregated, and we render that as HTML. Finally, these results are available to all staff on our intranet and are used by individuals around the company, by teams and stand-ups, end-of-sprint reviews, planning sessions, etc. So why do we bother doing this? Our sims follow a games as a service model, essentially, which for us means we generally make one or more core releases per year, and we release DLC and updates throughout the year. Including games and DLC, last year we released 36 products on Train Sim World alone, so we're constantly trying to improve our workflow and processes. Because of this model, it's really important that our code bases are well maintained and that we take technical debt and testing very seriously. And because we're a content-heavy studio, it's critical that we empower artists and designers, so all content creators, to find and evaluate their own problems where possible. And this means less engineering support to resolve certain issues, so less overhead. In practice, we use it to identify performance regressions, make historical comparisons against specific builds, and evaluate overall performance metrics when project-wide changes have been made, for example, to rendering settings. It means that producers and dev managers can get an insight into how things are going without chasing. Creators can get an early understanding of their content without having to test builds themselves, and it's especially useful for collaboration. So we've got three key sections to go through today. and I figured I needed to get some fish-shaped boxes in somewhere in this talk. So an example of load time testing. We quickly go through the whole process, including preparing your build, writing and then executing an actual test, storing those test results, and then generating useful output from the data. 2, we cover some of the novel work done to get more out of this internally, including our automation tool, which is a scripted process designed to link all of our testing stages together, how we handle test failures, and how we extend the local player class to better support our tests and to support testing in general. 3, we give a demo exploring some of our current test and presentation methods. Now, let me hand straight over to Jonas.
Thanks very much, John, and hello again. We'll go through our automation workflow in detail, all the way from preparing the build to the trouble developer looking at the results at the very end. During my part of the presentation, I will cover each of these steps a bit more in detail, as well as explaining how to write automation tests in UFO, so you get that part as well. Through this, I will use a test that measures load times as an example to make everything more concrete and more grounded in the reality. The first step of the workflow is to prepare the game build. And while this may seem like a rather trivial and obvious step, it's quite important. Before we do anything else, we copy the build down from our network build storage to the test host. As part of this step, we verify that the build is complete to make sure we haven't had any build issues. We could have had network outage, ran out of disk space, or anything. We want to make sure that we copy the latest working build down for each of these platforms. Once we have the builds for all the platforms on the test host, we then install them on the test targets, which are the consoles and the PCs that we will then run the tests on. On the surface, again, this seems quite simple, but it does hide a fair bit of robustness that you need to implement. In particular, we may need to use Orbis Control or one of the Xbox executables to reboot or reinitialize the kits at this stage. This is kind of true with any interaction that you do with the console. You may need to implement robustness around that. Now, the build is installed, we can just run the test, but to test anything that we have implemented, we need to write our own test. So in the next few slides, I will go through how to do that using UE4. There are a few basic considerations to make when writing automation tests for UE4. Each test type is a standalone class that is separate from your game logic, giving you the advantage of not polluting your game code with test logic. But like with anything in real life, in some cases, you need to make changes to the game logic to make your test work, possibly checking the GIS automation testing flag and then skipping things like UI prompts. An automation test contains two main parts, and I will cover both of them in detail in the example. But the first part are the latent automation commands, which contain the actual test logic. These are executed by the automation framework, which is entirely engine side, so you don't really need to write any code for that specifically. The second part of writing an automation test is the test definition itself, which is the glue that binds these latent automation commands together. And one thing worth noting here is that the test and command definitions can be placed anywhere within your folder structure. So you can choose to create one folder that's just called test and place all the test-related code in there, or you can place the code right next to where the source that you are testing, the functionality that you are testing is. For the next few slides, I will go through the details on how to implement a simple automation test that loads a map and logs the time it took to complete that load. This is a simple but important test. Load times are an important part of user experience in a game, and we need to know how long does it take to load into each map. And we definitely don't want manual QA to have to sit there with a stopwatch checking how long each of the maps take to load. It's very close to a real-life test. It's been slightly doctored for readability and compactability to fit it into the slides. And I want to mention that this is not the only way to define tests in UE4. There are some really convenient macros that are provided, but I did want to show the most general way and the way where you can more easily add data to the tests and in the automation commands themselves. So now, let's look at some code. The test in this example contains 2 latent automation commands, each of them short enough to fit on a single slide. It's that simple, really. The automation command on this slide travels to a map and waits for that to complete and then caches the duration of that load in a variable. So what do you have to do? Well, first, you have to create a subclass of the automation latent command, which is the base class of any latent automation commands. Again, this is where the macros would come in handy if you want to use the UE4 macros. Once you've done that, you declare your variables. In this case, we take a map name, we have a start time and a load duration, as well as a flag to say whether we've actually started the traveling or not. Now your class is defined, but to make it do anything interesting, you need to override the update function. This is called every frame by the automation framework, as long as you return false. Once you return true, this automation command is considered done, and the automation framework will move on to the next automation command. Our update function has 2 parts. The first part starts the traveling to the map. It checks the flag to see that we haven't started traveling, and then executes the open command, which starts loading into a map. Then it sets the flag that we've started traveling and caches the time at which we started. The second part is just waiting and waiting and waiting, hopefully not for that long, until the map is loaded. Once that's done, we just store the duration this took and return true, so that the automation framework knows to move on to the next latent automation command. Now, the second latent automation command takes the time we measured in our previous one and logs that to a file. Clearly, we could have made this part of the same command, but I wanted to show you the principle of chaining automation commands together, and also the idea that we should write our automation commands to make them as reusable as possible. Again, the first thing you do is to create a subclass of the iAutomation latent command. You declare your variables, which is the duration and the file we want to log this to, and then you override the update function. In this case, the update function will be called only once. We construct the path that we want to save the file to. We create the string that we want to save, and then we save it. And that's it. Done. Simple as that. Now, like I mentioned, the test definition is the glue that binds the latent commands together. And each test class defines a type of test and not a test instance, let's say. So in this example here, I've skipped some boilerplate code, which the compiler will warn you about anyway. So I didn't figure to clutter the slide with it. Again, the first thing you do, create a subclass, this time of F automation test base, which is the base class for any automation, any test definitions in UE4. Here, there are, again, macros to define this, but in this case, we're not using them. Then you declare the variables, and this is kind of a key part. We declare the duration here so that it can be used throughout both of the latent automation commands that we use, and we'll see that when I explain the run test function later. Once you have that variable there, you implement get tests. And get tests is called from the automation framework to get all the test instances of this test type that you want to be able to run. So it will fill out 2 lists. The first one called out beautified names. Obviously, you can choose the name of these variables, but this is the one from the engine. Gives you the names of the tests. You should fill that out with the names of the tests. The second one, out test commands, are the parameters that you want to send to those tests. In this example, we use a fictional class called test helper that has a function called get map tests. We do exactly the same thing. It populates those lists with tests that are specific to maps. We just have the name fishing in our test helper. Now, for each of those test instances, the automation framework will call run test with the parameters that you fill out in the out test command. As you can see here, all this does is to enqueue 2 latent automation commands that we saw in the previous 2 slides. The travel and wait, and then the log duration command. That's all it does, right? We've defined a complete and working automation test that's probably even useful. It's really as easy as that. Okay, so You've defined your test, you compiled your binary. All you need to do now is to run your game binary with a specific command line. The key part of the command line is the one you can see here that is highlighted as automation run test. This is picked up again by the automation framework in UE4, and this one will run a test called loadMapTest.mapA. We then enqueue a quit command because we don't want the game to just sit around once the test is done. Our performance tests are all run using the test configuration, and we're now talking about the build configuration, because in shipping, the automation framework is not defined, and in development, there's some performance overhead, in particular due to garbage collection verification that we want to avoid during our performance measurements. One important detail I kind of skipped over in the previous few slides is that if you're not using the macros, you need to add one instance of the test to the anonymous namespace so that the automation framework can pick it up. So if your tests are not picked up by the automation framework, this could be what you're missing. Okay. So you've implemented the tests, you've run the tests, they're all done. And what we do now is that we copy the results back from all the test targets onto the test host. In some cases, just a straight copy, like for screenshots, we copy them into the right folder structure and we're done. In other cases, for logs, we merge the data together so we only have one log with each data point being one test run. And just like any other interaction with consoles, we've added a fair amount of robustness to this step to ensure that we avoid easy-to-handle failures. Right. We have all the data on the test host now. So we run through it to generate HTML pages and then publish them to a local web server for easy access by all interested parties. You will see a demo how these web pages look in a few slides, but I just wanted to explain a little bit how it's done under the hood here. There's a one-to-one mapping from each type of test that we implement in UE4 to each type of analysis or HTML generation that we run in the tool, since each test is likely to want to display the data differently in the web page. And worth mentioning is that we use Google Charts API for chart generation, and we do generate quite a lot of charts because it's a really readable way to display data. All right. How do we generate these web pages, you ask? Well, first of all, we generate a tree-like structure that you see on the left on this slide. This is done in C#. Each node in this tree is an HTML element, and for each specific HTML tag, so say link or table or whatever, we create a subclass and override the functions for code generation. And as I click through here, you can see each of these nodes corresponding to a part of the page. So that's the whole page. You have the header table, then you have the main table, etc. You have table on the left, target list, etc. The charts on the right, split down. Once you have the tree, we traverse it depth first. And whenever we reach a new node, we add the preamble for that node, the preamble HTML code. So now we add the HTML. Whenever we reach a leaf node of the tree, we add the entire thing because that is basically the same thing as reaching it and leaving the node. So we add the table and the slash table. And then we carry on traversing the tree down depth first. When we leave a node, as in we traverse up the tree, we add the post amble. So you can see that I add the slash list, the slash table, the slash another table, which is outside of that table. And last but certainly not least, the slash HTML. That's the entire web page. Now, and that's it for the workflow. For the next few slides, I will go through some implementation details that I think you will find interesting. We've automated this entire workflow using an in-house tool that we wrote in C#. So there's no need for any manual intervention at any point throughout the pipeline. The tool is configured using a set of JSON files, which means we can easily tweak each step without having to change any code. All we do is to change some JSON data. You can see a snippet here of the test config, which is a list of tests that we want to run. And importantly, most, if not all, of the steps that we run in this automation tool will take some time to complete. And we want to be able to run multiple concurrently. So for this, we use the async API in C#, which is really convenient and easy to use. I would recommend it. In addition to performance testing, we handle test failures. This is far from complete coverage, but it comes almost for free with what we're already doing. It's kind of incidental. And it has uncovered some subtle errors that we may otherwise have missed. So what do? We just run the performance test as usual, but whenever a test fails, which generally happens in one or two ways, either the test times out, i.e. it's taken way too long, longer than the allotted time we've given for it, or there are errors in the log. The errors in the log are given to you by UE4, so you don't really need to do that. If there are errors in the log, the test will be considered a failure. When this happens, we do four things. We copy the game log back to the test host. We then parse that log to extract and format any errors in a more digestible format. We then link to that parsed log and then formatted log on the overview page of our website, which you will see in the demo soon. And once that's done, we also copy the crash dump back for further analysis. In this case, it's actually just manual analysis by a trouble developer at the end who's looking at the crash dumps. But it's still useful because we get another tester that doesn't really use up any person's time. So in addition to writing our own tool and writing our own tests, we have also created a subclass of ULocal player. We do this so we can override the exec function in this class, which allows us to easily add our own exec commands. And these exec commands handle the communication from the automation tool to the game binaries, so we can remove dependencies between these two code bases for things like data path or target frame rates. We definitely don't want to have to change code in two places because we want the data to be stored in another location. Of course, you can see here that these are quite specific to the testing we're doing, and you're absolutely right. But I would like to give you a key takeaway from these exec commands, and that is that each test run should have its own unique ID, and each data point that you store should be associated with one of these test IDs. This makes the data processing so much easier. Now, that's it for the implementation details, and now moving on to the demo.
Now that you've seen how our automation workflow is implemented, I would like to show you a demo of how we present the data. The initial page is an overview of all the tests on all platforms, where each platform has a list of tests, a list of test failures, and some selected data points that we have chosen to indicate potential problems. I will do a deep dive into the fixed location FPS tests on Xbox One. When I click on Fixed Location FPS, it brings me to an overview for that specific test on the selected platform. On the left, you can see a list of all maps sorted by average FPS, as well as some data that shows the extreme highs and the extreme lows, as well as the increase and decrease in FPS. On the right, you can see a graph of how the FPS has changed over time across the entire game for this platform. Each column in this graph corresponds to one test run, which we normally do nightly. If I click on one of the lakes in the list, and I will pick Ebro because it has the lowest FPS, it will take you to the data for that lake only. On this page, the left pane has a list of all the Xbox One test targets, and as you can see, we only have the one named Fisher5. On the right, there are three graphs showing the average, the lowest, and the highest FPS. And you can see how, in the graphs, you can see how it's changed the FPS over time. Again, each column corresponds to one test run. So far, we've seen charts of how the frame rate changes over time, but if I now decide to click on Fisher5, i.e. the target name, it will display the data in a slightly different way. What you get to see here is a heat map of the FPS in this lake. Each frustum corresponds to one test location. Let's pick a red one as an example. This one. When I hover it, you can see that there's some data displayed on the right hand side, such as GPU, game, and render thread times. This is the data for this location in the most recent test run. And when I click it, it opens a pop-up with more information. Here on the left, we can see a graph with how the FPS has changed over time for this specific location. Hovering over any of the columns displays the same data we saw before, but for that specific test run. So you can go back through time that way. If I click one of the columns, you can hopefully see how the screenshot on the right-hand side updates. This means that when there's a drop in frame rate, the artists can go into this web page, into this tool, and compare the game before and after the drop to figure out what has gone wrong, which is quite a powerful tool for them to have, and it doesn't require a programmer to analyze anything. And that's it for the demo. Now back to John.
So the key takeaways from using the automation framework are, once you get into it, it's really easy to use and quite powerful. But getting the whole process working in a fully automated manner really is a key investment. Otherwise, I think the process will pretty quickly be gathering dust. So putting that whole pipeline together and automating it is really key. So how do you decide on what to do next? How do you decide on what to test, and how do you present it? So a good place to start is to choose a simple test and metric, something that your game is struggling with, and start there. Presenting that data in a way that's useful but still deep enough for all users of the system is actually pretty difficult. You really need varying degrees of abstraction relative to the person viewing. You don't have to build a fancy UI for all tests at all. Our daily results are just a small subset of what we tested. That's what we render to that, to HTML, mostly to catch regression issues between builds. But building one-off tests is really common. So we've actually used it to reproduce bugs that have been really difficult to find manually. One case, for example, was we had a build to test where we teleported all over the map to find a difficult to reproduce concurrency crash. As a quick note, we have experienced some pain points running tests on consoles. Regular OS updates, typically from Microsoft, cause issues. The console is then often left in a bad state, needing a manual reboot from a controller button press, typically from Sony. This is made quite a bit worse with the pandemic lockdown. And our personal favorite, is when someone walks too close to a console and it decides to turn itself off. This, perhaps unsurprisingly, is a bit better with lockdown. So now I'm just going to quickly go through what we're currently working on. We're looking at useful ways to provide more depth to our daily testing, starting by recording more detailed performance metrics in general, such as draw call numbers, geometry and shader complexity. And we'd really like to give a better analysis of pain points, essentially picks, razor and render captures when required. We're also keen to perform daily tests on more complex gameplay features, such as multiplayer and multiplayer performance, fish catch rates, simulation accuracy. Obviously, this is just on these are just examples for the fishing game. So our current solution generates daily static HTML pages, but we're moving to writing directly to a database and generating dynamic content. Another area that we're focusing on is generating richer and more insightful results. So we're looking at parsing tagged source control commit messages from a build and highlighting major changes in those commit messages with explanations for possible performance drops, etc. So that means actually inserting tags into those commit messages. We'd also like to allow users to flag and annotate results from their browser to query and explain specific issues, so like a feedback loop straight away. Hopefully this means a clearer picture for those responsible for delivery in the studio. We currently use some basic email reporting, but more specific issue reports going out to the relevant people and hooks for Slack, Teams, etc. would be really useful. We're keen to exploit the integration of results back into the editor as well, along with basic suggestions from an analysis of the data. A further expansion of that idea, would be to provide more insightful suggestions generated by a supervised learning model. We're working on adopting Gauntlet into our pipeline to replace parts of our DTG automation tool. And finally, it'd be really hard to convince everyone in the studio that the time you're spending writing and maintaining tests would not be better spent making your game. It's hard to convince people of that. So we're keen to develop some metrics to evaluate our tests. In her talk last year, Jessica showed some great results evaluating bug numbers over their project lifecycle. But with this sort of analysis, it can be difficult to demonstrate statistical significance of those results and then establish causation. So we're really open to ideas here. And yeah, thank you very much for listening. And we're around for Q&A straight after this talk.